Hi, I'm Paul Kyogan from GKTuition, and in this video I want to go through Leaving Cert Higher Level exam question. Now the question I'm going through is 2015 Paper 1 Question 8. In this question we're told that an oil spill occurs off the coast and that the oil is spilling into the water at a rate of 4 by 10 to the power of 6 centimeters cubed per minute. So for A part 1 I just need to fill in my table. They started off by giving me the first value, so if it's going in at 4 by 10 to the power 6 per minute, then obviously after 2 minutes the volume is 8 by 10 to the power 6. Notice in my table it tells me the volume is given by 10 to the power 6 centimeters cubed. So 8 means 8 10 to the power 6 centimeters cubed. So after 1 minute it's 4, after 2 minutes it's 8, 12, 16, so we're just adding 4 each time. So what you should recognize is that this is a linear pattern. And then for the second part of the question, we're asked to graph that. Now obviously mine is a bit rough because I don't have a grid, but yours, obviously you want to do it as accurate as possible. And when you recognize that it's linear, you should use a ruler to join up your points. So basically just after every minute, it increases by 4 by 10 to the power 6 centimeters cubed per minute. For A part 3, we're asked to write an equation to describe the volume of oil in the water after t minutes. So come up with a formula to describe what's happening in this table. How did I work out the volume after 6 minutes? Well, that was easy. I multiplied 6 by 4. In this case it was 6 by 4. How would I do it after 100 minutes? After 100 minutes it would be 100 by 4. Because the volume is consistently increasing by 4 by 10 to the power 6. So it's just, your first instinct would be that it's 4 times t, where t is the number of minutes. However, don't forget that the volume, it's actually increasing by 4 by 10 to the power of 6 every minute. So when you're doing this, you have to actually write it as 4 by 10 to the power of 6 multiplied by t, where t is the number of minutes. So let's say t was 50. After 50 minutes, to work out what the 50th figure would be here, it would just be 50 multiplied by 4 by 10 to the power 6, and no, it was 200 by 10 to the power 6. In B part 1 of this question, we're told that as the oil spills, it forms a circular oil slick, which is 1 millimeter thick. We're asked to find an equation for the volume of the oil slick in terms of ore. Okay, so now the shape of the oil is really important here. It tells me that the oil is forming a circular shape above the water, but the circular shape is 1 millimeter thick. So I want you to recognize that a circle is a 2D shape. A circle refers to a two-dimensional shape, whereas this one I'm told is 1 millimeter thick, which means clearly the shape I'm dealing with is not two-dimensional. If I have a circle that's 1 millimeter thick, that means I'm dealing with a cylinder. So even though the question says it's a circular oil slick, you need to recognize that the shape of the oil is cylindrical, because it's a circle but it's 1 millimeter thick. So in fact, in this question I have to get the volume of a cylinder. Now I'm given the height, or I'm given the thickness of the cylinder in millimeters, and I'm asked to find it in centimeters. So you should recognize that 1 millimeter is the same as 0.1 centimeters. In other words, I just divide by 10. I know that the height of my cylinder is 0.1 centimeters. And I know that the radius is r. Once I've got all of this, it's relatively straightforward to come up with an equation for the volume of my cylinder. From my maths tables, or from my log tables, I know that the volume of a cylinder is V is equal to pi r squared h. So I just need to sub in my values and I'll work it out. So in this case I can say that the volume of the oil slick is pi, and instead of r I'm just going to sub in r, so it just becomes r squared, and instead of h I'm going to sub in 0.1. So my final answer in this question is just that V is equal to 0.1 pi r squared. And that is the volume of the oil slick. B part 2 of this question asks me to find the rate in centimeters per minute at which the radius is increasing, when the radius is 50 meters. Okay, so there's a few important buzzwords here that you need to hone in on. The first one is the rate. I need to find the rate at which the radius is increasing. When you see the word rate, the first thing that should come into your mind is differentiation. I need to find the rate at which the radius is increasing. Now, if it said find the rate at which the radius is increasing relative to volume, that means find d or dv. If it said the rate at which the radius is increasing relative to area, that's d or dA. But if it doesn't specify, that means it's d or dt. Or in other words, it's the rate at which the radius is increasing relative to time, because everything changes relative to time. So another giveaway there is the units. It asked me to find it in centimeters per minute. Now clearly the radius is measured in centimeters and time is measured in minutes. So you should recognize that they're asking you to find d or dt, the rate at which the radius is increasing. And this will be centimeters per minute. In order to find d or dt, I'm going to need to use two other derivatives. Now you should look at what we've previously worked out in order to figure out which derivatives we need to use. Previously, I've worked out v is equal to 4 by 10 to the power 6 times t, and I've worked out that v is equal to 0.1 pi or squared. Now you should bear that in mind. If I get the derivative here, I'd have dv dt, and if I get the derivative here, I'd have dv d or. So in order to get d or dt, well then clearly on the top of one of these fractions I want to have a d or. And on the bottom of the other fraction I want to have a dt. So I want to have a d or on the top and I want to have a dt on the bottom. Now I can get d or dv from this equation here. So it must be that I'm getting d or dv, and I can get dv dt from this equation here, so this must be a dv. So now I have a d or on the top, a dt on the bottom, and clearly if I multiply d or dv by dv dt, I'd be left with d or dt. So I think this is the key for a lot of students. It's just, if you can work out that line, the rest of the question is relatively straightforward differentiation. Now we have to look at our previous answers and we can work out our d or dt. So with my first equation, I can just differentiate. The derivative dv dt, the derivative of 4 by 10 to the power 6 times t is just 4 by 10 to the power 6. So I know my dv dt is 4 by 10 to the power 6. Now, if I differentiate straight away here, I'm going to get dv d or. Okay, remember that pi is a number. Pi is a number in this case. So my variable in this case is my or squared. So I bring the power in front. That means it's 2 multiplied by 0.1 pi, which gives me 0.2 pi. And then I decrease the power of or by 1, so it becomes or to the power of 1. So I know dv d or is 0.2 pi or. However, I don't want dv d or, I want d or dv. Or in other words, I want the reciprocal of it. So all I need to do is flip my fraction. You should view this as 0.2 pi or over 1. So if I flip both of my fractions, that means that d or dv is 1 over 0.2 pi or. So now I know d or dv and I know dv dt, so I can just sub straight in. So d or dt, the rate at which the radius is increasing, is d or dv, which is 1 over 0.2 times pi times or, multiplied by dv dt, which is 4 by 10 to the power 6, and let's just call it over 1. Now it asked me to find the d or dt when the radius is 50 meters. But you have to recognize that everything we're dealing with is in centimeters. And it asked me to find this in centimeters per minute. So clearly there's 100 centimeters in a meter. So 50 multiplied by 100 is 5,000. So that means the radius that I'm going to use is 5,000 centimeters. So I just need to get this value, except instead of an or, I'm going to sub in 5,000. Which means in this case, my final answer, d or dt, well on the top I just have 4 multiplied by 10 to the power of 6. And on the bottom I have 0.2 pi, and instead of or, I'm going to sub in 5,000. Now all we have to do here is just plug all of this straight into our calculator. And if you plug it into your calculator, you get 1273.2395. So the question doesn't specify here, so let's round it off to 2 decimal places. I get 1273.24, and again it's the radius divided by the time. The radius is in centimeters and the time is in minutes. So it's 1273.24 centimeters per minute. So that's my final answer in this case. Again, I think the key to these questions, just make sure, listen to what I said about this, make sure you understand where we're getting that line. Because once you can get that line, the rest of it is relatively straightforward. In part C of this question, we're asked to show that the area of water covered by the oil slick is increasing at a constant rate of 4 by 10 to the power 7 centimeters squared per minute. Now, first of all, to show that something is increasing, to show that something is a constant rate, that just means that it's going to be a constant. A constant means a number. So 6 is a constant. Any number is a constant. For example, the dr/dt in this case is not a constant because it depends on the variable or. So to prove that something is a constant, that just means that my answer is going to be a number with no variables in it. Now the question has asked me to prove that the rate at which the area is increasing is a constant. So that means I need to get the a dt, the rate at which the area is increasing, and it asked me to get it in centimeters squared per minute. So again, notice that the units are a giveaway. Centimeters squared is area, minute is time. Okay, so another very important thing you have to worry about here. In part B, I was talking about the oil slick, and the oil slick was a cylinder. However, in part C, I'm talking about the area of water covered by the oil. If you imagine the shape of the water that's covered by the oil, well, the oil is covering the water in a circle. So the area of water covered by the oil is a circle. So this time, you have to recognize that we're dealing with the circular part of the water that's covered by the oil. So just that'll come into play in a minute. So I need to get the a dt. And clearly in the previous part of the question, I've worked out the dr/dt. So let's assume we need to use that. I want to have a dt on the bottom at some point, and I want to have a dA on the top at another point. So I want to have a dA on the top, and I want to have a dt on the bottom. If there's a dr on the top here, then clearly I want a dr on the bottom here. Because dr/dt multiplied by dA dr will give me dA dt. But it's getting the dA dt that's really important. I'm no longer dealing with a cylinder. I'm talking about the area of water covered by the oil slick. The oil is covering the water in a circular shape. So to get the a dr, I want to go to my log tables, and I want to go to the formula for the 2D shapes, and I want to get the area of a circle. The area of a circle is a is equal to pi r squared. So now it's going to be relatively straightforward to get the a dr. I just have to get my derivative. So the derivative in this case, the a dr, well, I just bring my power in front. So r to the power 2, the 2 comes in front, and it becomes 2 pi r to the power of 1. So straight away I know dA dr is 2 pi r. So I know dr/dt and I know dA dr, so I can just plug them straight in. So that means the a dt, the rate at which the area is increasing, is 4 by 10 to the power 6 divided by 0.2 times pi times r multiplied by 2 pi r. Now this one works out really nicely because I've got an r on the top and an r on the bottom. I have a pi on the top and a pi on the bottom. 0.2 goes into 2 10 times, so it's actually just 4 by 10 to the power 6 multiplied by 10, which is 4 by 10 to the power 7. So the a dt is 4 by 10 to the power 7. Now just notice there's no variables here, there's no or in my answer, so this is a constant. So the rate at which the area is increasing is a constant. And that comes into play now in the last part of the question. Again, units are really important in these questions. So area is measured in centimeters squared and time is measured in minutes. So my final answer there is 4 by 10 to the power 7 centimeters squared per minute. Okay, so for the last part of this question, we're told that the oil spill began 1 kilometer from the nearest land. And we're asked to find how long will it take before the oil reaches the land. So let's just imagine, let's draw a rough sketch here. Let's say this dot represents where the oil spill began. And I know that the oil is spreading out in a circular shape. So I know that when it touches land, the radius of this circle must be 1 kilometer. So the radius of my circle here is going to be 1 kilometer. And I want to know how long will it take before the radius is 1 kilometer. Remember, everything we've been dealing with, my dr/dt and my dA dt, they're all in centimeters. So in this case, I need to convert my 1 kilometer into centimeters. To convert it to meters, I multiply by 1,000, and to convert meters to centimeters, I multiply by 100, which means that 1 kilometer is actually 100,000 centimeters. So I want to know how long will it take before the radius of my circle is 100,000 centimeters. So that's my radius. However, the radius is absolutely useless to me because I've worked out that the rate at which the radius is increasing is variable. There's a variable in it. It depends on the radius. The rate at which the radius is increasing is not a constant. So in fact, that's no good to me. However, in part C, I worked out that the rate at which the area is increasing is constant, which means what I actually want to do is find the area of this circle. Once I know the area of this circle, and I know it's increasing by this much every minute, I'll be able to work out how long that will take. So in fact, right, I know the radius of my circle is 100,000, but I'm actually concerned with the area of my circle. The area of a circle is given as pi r squared. So if we plug this in, that means I get the area as pi by 100,000 to be squared. And if I plug that into my calculator, when the oil reaches land, I know that the area of water covered by the oil, 100,000 to the power of 2 is 10 to the power of 10. So it's 10 to the power of 10 by pi centimeters squared. So I want to know how long will it take before the area of this circle will be 10 to the power of 10 pi centimeters squared. And I know that the area increases by 4 by 10 to the power of 7 per minute. So I want to know how long will it take in order for the area to reach this. So if this is the area I want, and this is how much it increases per minute. But think about it. After 1 minute, I know it'll be 4 by 10 to the power of 7. After 5 minutes, I'll multiply that by 5. I know it's 20 by 10 to the power of 7. After 50 minutes, I'd multiply 50 by this, so it'd be 200 by 10 to the power of 7. So if I know the actual area, what I want to do is I want to divide my dA dt into this. I want to know how, if I increase by 4 by 10 to the power of 7 every minute, how many minutes will it take for the area to become 10 by 10 to the power of 10 times pi. So 10 to the power of 10 times pi divided by 4 by 10 to the power of 7, I just plug that into my calculator. And when I do that, I work out that after 785.39 minutes, the area of water covered by oil will be 10 to the power of 10 times pi centimeters squared. Just notice the question asked me to leave my answer to the nearest hour, which means if I've got minutes to convert to hours, clearly I want to divide by 60. So if you divide that by 60, works out as 13.09 hours. If I round to the nearest hour, I get 13 hours. So after roughly 13 hours, the oil is likely to reach land. Okay, so again, I hope this video made sense. If there's anything you're unsure on, then just let me know in class and I'll try and explain it differently.